Hey, Christian. So, Christian, what do you think about the extra credit? Is it getting too unproductive, or
No,
is it too many questions? Or
no, I keep forgetting actually.
oh no, this was not a complaint against that. No, no, no. I didn't even notice that.
Yeah, no, actually, you just reminded me, 'cause I think there was one from the other day that I forgot.
No, I was just wondering, is it too many extra credits and it is not really useful, like thought-provoking questions or
Yeah, sometimes it seems it's
too
yeah
many?
a little bit much, but I think they're helpful mostly. More often than not, they are. But
Like if there is no due date, would that be more useful, something like that? And any feedback on that?
maybe if I could sit down and do like a bunch of extra credits at once, like at the end of the week or something.
That's better, like, or weekly submission instead of,
Uh-huh.
that might be.
Yeah, because then they're all like somewhat related to and
Yeah.
yeah.
Yeah. Because it's not necessary that you sit on the course every day, right?
Yeah, sometimes it's hard to find time.
Yeah. I will think about it. Yeah. As of now, I think it's all set, but maybe in the future, maybe all in one day. So, Borden, do you have any comments on extra credit? How it is made due every quarter? Is it productive? Is it not productive?
You were saying correctly, like once a week, like have it at the end of the week.
Yeah.
I wouldn't be opposed to that. Sometimes I forget to do it just because some classes you don't have it, some you do. And then I get busy with other stuff, so it's not really in front of my mind.
Okay. Yeah, we'll think about it. Curtis and Matt, is there any comments you have on extra credit problem, the way they are made due?
No, no questions.
Could you repeat? I think I missed it.
Yeah, I said no questions.
No, I think what I asked was that, do you have any feedback on the way extra credit is posed, like the way would it benefit?
I mean, I think the way you're doing it is fine. You make it pretty clear in the lecture for the most part. And if there is some questions, usually you try and write it out.
Okay. Okay. Curtis? We cannot hear you, Curtis. Maybe it's muted. You don't realize, or
I was away. What were you asking?
Oh, I see. So I was asking, is there any feedback you have on the way extra credit is made due? Like anything you might want to change this halfway down the semester? Like, is it too many extra credit problems, or would it help if it is made due once in a week or something like that? Any changes you would like, or it's okay the way it is?
I'm all right with how it is right now. It hasn't been too bad, but maybe like once a week would probably be better, like in terms of just having everything like at a single time.
It might be convenient, you're saying. Okay, that's it. I might consider that. Yeah, I'll think about it. We'll be starting next week anyway. Okay, thanks. Like homework 8, that's due October 7. Which is a Wednesday. And I think everything you need is there. Yeah. I think so, yeah. Midterm 2, oh, before that, there's no class. No class on Monday. Midterm 2 on so midterm 2 is an in-class on Friday. I think we are 6 of us, so this room can accommodate 6 of us, so I will have to get out, so I'll check something like that to keep the open. We'll stick to the rules. Okay, we did Legendre polynomials, so remember that. So the way we introduce Legendre polynomials is, so let's see, this is called the generating function. I didn't define it this way, but generating function, this is for Legendre polynomials is, this is the square root of this, so this is 1 minus, let's say 2xt plus t squared. So that's equal to sum over this from L equal to 0 to infinity and t raised to L and PL x. And what we did last time, x was for cosine theta, and t was basically r prime over r. And the square root there was showing up as r minus r prime. We said this is the same as 1 over r squared plus r prime square minus 2 r prime cosine theta. And then one can write this as 1 over r times 1 plus r prime square over r square minus 2 times. And then you see that structure in there, right? We said this is the electric potential due to a point charge when the charge is placed at r prime and the observation point is r, and it has this structure, and which basically involves this expansion. So do a Taylor expansion in T. So that's your Taylor expansion in T, and the coefficients of that are called generating. The coefficients of that are called Legendre polynomials. This is a Legendre polynomials of order. These are one kind of special functions. There are various special functions that you will see. How many special functions have you guys seen or come across before? Any other special function you can think of? Have you guys seen, have you taken quantum mechanics, or are you taking quantum mechanics? You'll be, yeah, so you're not. Partial differential equations, have you guys done? And in that, any other function you have come across? Fourier series, Fourier functions are also actually special functions, but they are the first ones you encounter something more. So, yeah, so it's a good, so this is a, let's say, extra credit just to explore what these are. So just to make you guys explore, look for, so usually a special function has to do with a differential equation. That is always a, so let me list. So this is a special function, various special, many of them, but some of them keep coming again and again. And there is a differential equation associated with it. That means to say that whenever you encounter a certain differential equation, you know that, oh, this is the solution. Right? So first is Fourier function. And your goal here is in the extra credit to list, just find out, go on the internet and find out what is the corresponding differential equation that leads to this. There is Legendre polynomials. That's what we're doing. Then there are Hermite polynomials. Hermite polynomials are when you solve the harmonic oscillator problem in quantum mechanics. It is expressed in terms of Hermite polynomials. Legendre polynomials, and then the spherical harmonics. Then there are Bessel functions. And so there are many more, but it's not a huge list, but that's probably double of this, or maybe triple of this. There's a fixed number, or there are very few special functions we know, and then you can generalize it. That is hypergeometric functions, and so on. So it's kind of a nice thing to be aware of. Yes. Zeta function is not, as far as I know. Good point. Yes, zeta function is not a special function. Why is it not a special function? Because yeah. So the notice that here, so there is this PL of x, right? So this is a, for each L there is a function, right? So they act like a complete set. So if you give me all the L's, then they act like a function space. They act like a unit vectors of a function. So any function can be expanded in W. Zeta function doesn't have the L, so it's just zeta. So it's just a function. So in that sense, it is not there. But there might be associated zeta functions maybe, and you might be able to build such a thing. I'm not sure. Yeah. I remember having thought of writing down a differential equation. Yeah, I don't think so. I'm not sure. Okay. I think it's not that. Like Gamma function also, you don't write a differential equation for that. Or I never encountered it. And that's primarily because of this. It doesn't form a complete set. So good question.
Yeah, that helps to
Yeah.
separate.
Yeah, it doesn't form a complete set. So these functions form sort of a unit vectors in an infinite dimensional space. Okay, so that's a good thing to know. Whether whatever subject, whatever field you're going to be working on, that's a very useful. If you're going to be anything associated with whatever we are learning, and something or the other will come up in whatever kind of job you are working on. You have to analyze something. So it's a good thing to be aware of. So that's good. And most of them will have a generating function. They will always have a function using whose coefficients of expansion will be defined as the function. So that's how typically it works out. So, so that's the generating function. And then we said, yeah, we also argued that P0 of x is 1, P1 of x is x, and P2 of x is equal to, what was it, 3 by 2 x squared minus 1 by 2. Right? And we had a procedure to evaluate that, but that was a pretty messy procedure or very mechanical. Is there a general formula for this? You would like to know if is there a general formula for this? Yes, there is a general formula. So let's try to evaluate that, right? What we did was we basically Taylor expanded this, right? So let's do the Taylor expansion and try to get a formula for this. Okay, so let's first begin with 1 over 1 minus x square root, right? So this is of the form. So whatever this quantity, if I were to write as, let me not write it x, let me write y, so that you don't confuse with the x. That's equal to 1, so there's a minus 1 by 2, and there is a minus y, right? So that's 1 plus 1 by 2 times y plus 1 by 2 factorial of 1 by 2 times 1 by 2 minus 1 by 2 is 1 by 2 plus 1, correct? Is that correct?
Oh, I thought the second term with the y was going to be plus.
But there's a minus half here,
Oh,
right? So plus y will be, right? So it is 1 plus y raised to n is 1 plus n times y plus n times n minus 1 over 2 factorial times y squared and so on.
So
Right? So yes.
should be minus somewhere, right?
Because that's what I was explaining. So this is n times y, right? So n is minus half here, and there's a minus y. Correct. So for example, 1 plus minus y of minus half will be 1 plus minus half
Oh, okay.
of minus y, right?
Because it's minus half in the beginning.
Yes, exactly.
Okay.
Right.
I thought it was probably.
Yeah. So like this is the formula, but then we are doing minus y and there is a half, which is minus. So it kind of cancels out. Similarly, there is 2 minus signs here. Y is also 2 minus signs, they all cancel out. So this is 1 by 2 plus half y squared and so on. Agreed? Let's write this as a series, right? There's a pattern in there. So let's write that as a series. So this is L equal to 0 to infinity. So that is L equal to 0, 1. So there's y raised to L. There is 1 over L factorial. And then I'm doing 1 over 2, so let me explicitly write this, 1 over 2, 1 over 2 plus 1. If I was going to L, I had to go 1 down, right? So it is keep going until 1 over 2 plus L minus 1. Correct. So there seems to be 2 raised to L terms in this because 1, 2, L minus 1, and then the first one was 2 raised to L. So that's the same as L equal to 0 to infinity y over 1 over L factorial. Pull out the 1, 2's out. And then what am I having? The first one is 1. Next one is 2 plus 1, 3, right? Next one will be 5. And so on until this one is L minus 2. So that's up here. So 2L minus 1. So let me plug in a 2 here, 4 here, all the even numbers I provided from the top, so I have to divide it down there, right? 2, 4, so on. And the last one will be 2L. So this is 2L. But then I can again pull 2 from each one of this, the L of them. 1, 2, yeah, L of them, okay? And that becomes an L factorial, right? So this becomes L equal to 0 to infinity y raised to L. On top we have 2L factorial. In the denominator we have that is 2 raised to L here, 2 raised to L there, so that's 2 raised to 2L. Right. And then there is L factorial. There's another L factorial, that's square.
Good question.
Yes.
In the equation above that, why is it not 5 to the 6th?
5 to the, no, this is not 6. So what I did was, this denominator was not there. Okay, let me redo it. Okay. So this was, there are 2 here, 2 here, 2 here, there are denominators, right? I collected them. Correct? So now I'm writing the numerator. The top one is 1. When I multiply this 2 here, 2 plus 1, 3. Right?
Mm-hmm.
Next one will be 5. And so on. The last one is 2L minus 2 plus 1, that's 2L minus 1. And this is not there. Okay, great.
Mm-hmm.
But that's not a factorial, right? I'm missing 2, I'm missing 4, I'm missing many.
Okay, so you put it on the top and the bottom.
Exactly. So I put in a I put in a 2 in here, I put in a 4 in here, and I put in a 2L in here, and then I put it both. That's better, I think.
Okay. Could you still like put in a 6 even though it's not necessary?
Yes, yeah, put in
Okay.
6. Yes, exactly.
That's what I'll-
I want a 6 there. Yeah, and it's understood that I'm proper. I am filling in all the things that are missing. Right. And that comes out to this. Right, so basically, I just manually did that, and so this is what it is. So that formula we want to use to expand this, right? That will give us a series in this, and then I want to capture the coefficient of t raised to L. That's my goal. Right, so we are still away. So let me do that. Any questions at this stage? So first step. Right. So we call it I, right? We'll write it again and again. So this is I of x comma t, right? Actually, since it's a generating function, often it's called g. It's a generating function which is x of t. Okay, so it's equal to g of x comma t will be equal to summit. So this is L equal to 0 to infinity. But y now is 2xt minus t squared. So put all these things there. 2L factorial 2 raised to 2L L factorial squared. And y now is 2 times xt minus t squared and raised to L. Yeah. This is again an expansion. This is a binomial expansion, and L is always an integer in this case. So it won't be an infinite series, it will be a finite series, right? So A plus B, so let's write it as A plus B raised to L would be equal to, we go from L equal to 0 to all the way, sorry, it's not L, so this N, so let's say M. Yeah, so let's say M equal to 0 to L. Okay. For example, if it was squared, I'll go from 0, 1, 2. Right? There are 3 of them. So this will be L factorial. Correct? L factorial divided by M factorial divided by L minus M factorial. And then there is A raised to L minus M and B raised to M. Right. For example, if you can check this for L equal to 2, for example, and it is 2 factorial, so only second term. So that's a general formula. Is that familiar, roughly? No, not familiar. Okay. Okay, so we'll check it. Right. So this is called a binomial expansion somewhere. Is that name familiar?
Yeah, but I don't think that's how I've seen it before. Maybe just not explicitly in that notation. Yeah.
Binomial expansion. Yeah, so this is for integers. What I did earlier was applicable for any L. So this is for integer values of L. Then it is finite, right? So check it for L equal to 2, right? So let's check it for L equal to 3, right? Better. We'll do both. L equal to 2, then first term is 2 factorial divided by m is 0, 0 factorial, times L minus 0, so that's 2 factorial times a raised to 2 b raised to 0, plus 2 factorial divided by 1 factorial, a raised to 1, b, plus 2 factorial, m is now 2 factorial, 0 factorial, and a raised to 0, b squared. So, and these coefficients that you get out of this, that also has this nice feature. I think there's some triangle. It's called. So there's a nice pattern you can make for L equals 2, L equals 3, L equals 3. So you keep writing all these patterns, you see some nice structures. So yeah, so I'll let you guys explore that. So L equals 3 and some questions. Yeah. Okay. So I'm going to replace that with that. Okay. So this is equal to. Then now there are two sums, right? L equal to 0 to infinity, and this is 2L factorial, 2 raised to 2L, L factorial squared, and now comes the binomial expansion. This is equal to m equal to 0 to, I go only till L because it's an integer expansion, and this is L factorial divided by m factorial times L minus m factorial. A raised to, so this is 2xt raised to L minus m, and d is minus t squared, right? So capital of that. So minus t squared raised to m. Right? There's minus 1 raised to m, and there's 2t raised to 2m. So yeah, okay, so let's collect all this once more. Let's write it the way I want to write it. This doesn't depend on m. I can put this in here. So there's double sum here. This is L equal to 0 to infinity, m equal to 0 to L. One of the L factorial cancels. There is a 2, let's keep it as it is. So this is 2L factorial. Oh, there's a minus 1. Let me bring that up. So this minus 1 raised to m, 2L factorial divided by 2 raised to 2L. And there's L factorial, one of the L factorial cancels out, m factorial, and then L minus m factorial. Okay, so that's all the number coefficients. Let me separate t and 2x. So this is 2x raised to L minus m. Now t, there is a 2m, there is a minus m there. It is m plus L. It is t raised to m plus L. Here, notice t raised to L minus m is there, and then there is 2m.
Oh, okay.
So one of the m's cancel outside is L plus m. So that's your series. But we want to compare these, right? If I want to capture this PL, I have to get the coefficient of t raised to L there. But this is not t raised to L, this is t raised to L plus m. Okay, that's not convenient, right? So we have to do more work. Okay. So how do we capture t raised to L when the summation is from t raised to L plus m? Have you guys done any such things before? So notice, so you want to compare this, right? Expanding in L, you want to capture this coefficient. Surely there is some coefficient here, but that's not the coefficient of t raised to L. It is t raised to L plus m. So it is kind of shifted, right? So you got to manipulate or massage this more, right? So you got to work on this. So a standard procedure is to resum it, right? So relabel these quantities somehow. So let's do that. So, well, we lost someone. Matt, we lost Matt. Okay. Yeah. So Curtis, yeah. So hopefully the connection is okay.
I haven't had any issues.
Yeah. Okay. Good. Tell it again.
Do you like leave a comment?
Oh, it's comment. Yeah. Chat or something, right? Yeah. Nope. No chats. Yeah. Probably his internet just died or something. Okay. So let's see. How do we process this? Okay. So here's the trick. This is again pretty standard, but let's see this. So what are we doing here? So let's look at this L and M sum here. So this represents a discrete number set if you want. I'm going to show this as L. Right? So let me draw some lines here for reference. And let us say 1, 2, 3. What is sufficient? Okay. So that's L. So this represents L equal to 0 line. This represents L equal to 1 and so on. Right? So this is L equal to 2, 3, 4. Right? Let's say that's fine. Points. So I'm going, whenever I do L equal to 0, that's this point. For L equal to 0, M runs from 0 to 0. Right? When L is equal to 0, M is having only 1 point. So that's that point itself. So this is going to be my M. So this is M equal to 0, right? M equal to 1, M equal to 2, and so on. Okay. So for L is equal to 0, this has only 1 point. When L is equal to 1, M goes from 0 to 1. So that's these 2 points. And L equal to 2, I go 3 points. So you see the pattern that you're getting only half of the points in a quadrant. And that you go all the way to infinity in L, but along the M side, you don't go all the way to infinity, you stop at a point, which is a line there. So the summation scheme is start from here, go to the top, then start from here, go to the top 3. So we are going vertically up. But this is a sum. Who says that I should be going vertically? I can go like this. Right? As far as I have a nice order of doing it, that's perfectly fine. And that is a trick I want to use. There is an L plus M. I want to call this a new variable. Right? So you want to call L plus M to be a new variable. And let's call that N. L plus M is this means this implies that M is equal to minus L plus N. That's an equation of a straight line with slope minus 1. And this is your y-intercept. Right? So how do I interpret that? So this is my lines. Right? So that's my, these are all y equal to So slope, negative slope here. If that helps, I don't know. I think that's reasonably clear. You remove this. Okay, so this is my increasing n. This is n equal to 0. This is n equal to 1, n equal to 2, and so on, because they intersect at this point, right? N equal to 1, n equal to, so that's your y-intercept. Like that is how I'm reading my n. Agreed? Is that clear? So I'm going to, I'll fix my n and then run this way. So I'll collect these points. So for n equal to 0, I have only 1 point. N equal to 1, also I have only 1 point. N equal to 2, also I have 1 point. Sorry, 2 point. Then 2 point, 3, 3, again there will be 3. So it seems like every consecutive once I get this a certain number of points I want to add. What's the other choice I will keep? So once these are diagonal, why not choose the other one also diagonal? So I'll fix this to be, that's going to be my other variable. Now what is those variable? Clearly, I will pick this to be m equal to plus L. And let's say that's k. So that means that m plus m minus L is equal to k. And what are these lines? This is k equal to, so again slope, right? So this is k equal to 0. The next one is k equal to minus 1, k equal to minus 2, and so on. So it seems like you're running from k equal to. Is that clear how I'm getting this minus 1, minus 2, so on? Like it is, I'm looking at the y-intercept. Where is this cutting this? Right, that's a minus 1, this is minus 2. So whenever, whatever this value is, that's what is coming down in this. Okay. So that's your change of variables you want to. So wherever L plus M comes, you're going to write N and so on. So we want to replace this L and M's. So let me do this add and subtract, right? So if I were to add these two quantities, so M becomes N plus K over 2. And L becomes, I want to subtract that. So L becomes N minus K. So I will subtract that n minus k over 2. So that's my replacements. Okay. Is that clear? So now I write that again, right, in terms of these new variables. All this so that I can change this L plus M to a single variable n. Then I can compare the coefficients. Okay, so this is equal to, I have to run from the summation is whatever I set this way. This way I run from n equal to 0 to infinity. But for each n, my k runs only to, so the k limit is tricky, right? So let me just say this is k. Okay. So how does my k run? I'll fix that in a minute, but let me first replace all this. So this is minus 1 raised to m. M is n plus k over 2. Okay. And 2L. 2L is n minus k factorial. And 2 raised to 2 times L, which is 2 raised to n minus k. L factorial, that's n minus k over 2 factorial. M is n plus k over 2 factorial. And L minus M is L minus M is minus k factorial. seems like we're getting a negative number of fractions. Actually, that's not that because of this summation, the way things work here. So I'll see that in a minute. So it's 2 times x raised to L minus m. L minus m is minus k. And t raised to L plus m, which is m. Okay, so what does this k summation here mean? So let's see. So whenever n is even, let's say n is even, k goes from, so for example, 0, let's take some higher value, 0, then it is 0 and minus 2, then it is 0, minus 2, minus 4, and so on. So it seems like it is going from 0, minus 2, minus 4, and how far does it go? So this is 4, so that's until minus n. And similarly, n is equal to odd, k goes from, it starts from minus 1, minus 3, minus 5, and so on. Again, n is odd this time, so this is still goes to minus n. It's odd, it can go to Christian. So you have to look at this point here. So this is 0, 1, so on. Each one, how far does it go? It starts from here, then goes here. This, 2, this. So you gotta carefully see. Okay, am I being clear? Okay. So that's that. K in here. So let me. So it seems like this is. It's good to actually say that k is 2 times k prime. K is k prime is equal to k over 2. So then what happens is that this doesn't, so that is 0, 1, 2 until k over 2, 0, 1, 2, k over 2. And in fact, put a negative sign also. Then we don't have to worry about that. So this quantity here becomes n equal to 0 to infinity, and k prime goes from 0 to, actually I don't want to do that, sorry. I think I will do the following, because I want to start from 0. Let me do the following. Yeah. Give me another chance. K prime is equal to, what I want to start with is, if it is even, then I start with n over 2 minus k, right? If it is 0, right? So this is n minus 2, then it is minus 2. So if k is equal, so plus. Right? If it is 0, then it is minus 2. Then it's a, so this is n over, so k prime is equal to, first let me do n plus k. So that means to say, if I, instead of going this way, I'm coming the other way, right? So when n is equal to, so when k is equal to 0, k prime is equal to n, 0, n, then it is n minus 2, n minus 4, and at the end it is 0. I'm just going in the opposite direction, that's all. Instead of going this way, I'm coming that way. That's the only thing. And if it is odd, I start from n minus, so same thing, right? So this will be again n equal to minus 1. So this is n minus 1, n minus 3, and so on. And again, you will end with 0. And I want to also do get rid of this factor of 2, so divide this by 2. Let's do that substitution. So that has this feature that it either goes to the maximum when k prime has a maximum of either n over 2 if it is even, or it is n minus 1 over 2 if it is odd. So that's that feature that comes in, and then we are pretty close. So, 3 minutes. I think I can do this. K prime n minus k. So k is 2k prime. This k is equal to 2k prime minus n. So so n minus k would be equal to n minus of 2k prime minus n. So that's 2n minus 2k prime. Good. So this is 2n minus 2k prime factorial divided by 2 raised to n minus k, that is 2 raised to 2n minus 2k prime, n minus k over 2, that's n minus k prime factorial, and plus k over 2, so that's k prime factorial, and minus k factorial, that makes it n minus 2k prime factorial. Okay, all this, okay, and then 2x raised to minus k, k is n minus 2k prime. And t raised to n, t raised to n stays t raised to n. Right. Okay. Which means that since I've isolated t raised to n, I now know what is my, whatever sits in front is my Legendre polynomial, right? That's your definition of Legendre polynomials. Whatever sits in there. So this is L, so that is n, so it is actually Pn of x. So this is Pn of x is equal to 2. So I can even get rid of this 2, right? So I can get rid of this 2 also. So this is k, and I'd start writing instead of k prime, I'll just say k, right? K equal to 0 to n minus 2 if it was even, or n minus 1 over 2. This is if it was even, this is if it was odd. So there's a notation there that if it is if n is even, you run till n over 2. If n is odd, you run over n minus 1 over 2. So there's minus 1 raised to k now, 2n minus 2k factorial. That is a 2 raised to 2n, that is a 2 raised to n there. 2k prime, 2k prime cancel, so this is just factor of 2 raised to n. So that's 2 cancels out. And then there is n minus k factorial, and n minus 2k factorial. And x raised to n minus 2k. Curtis, do you have a class in the next 4 minutes? 5 minutes?
No, I'm free.
Yes or no?
I don't have any classes after.
Can I take 5 more minutes, then I can finish a few things?
Yeah, that's fine.
Question?
That's
Good.
fine.
Yeah, so it's just a few steps more than you can just finish it. And those who are watching, they can always take extra time. Yeah, so that's your definition of Legendre polynomials as a series, but notice that this thing can be written in a slightly different way. You can notice that d by dx raised to L of x raised to n of x raised to n 2n minus 2k will be equal to, you take derivatives of this, right? First derivative will bring down at 2n minus 2k, 2n minus 2k. Second derivative will bring down 2n minus 2k minus 1, and so on. And it will go on until, since there are n of them, so this will go on until n 2n minus 2k. Right, so the first one, so minus 1, right, minus n actually. Minus n minus 1. Okay, times x raised to n minus 2k. Right? Because after nth derivative, there will be only n left. Right? N of them will cancel out. That's the same as 2n minus 2k factorial divided by n minus 2k factorial times x raised to n minus 2k. That's cool because that's exactly the same expression that's sitting here. So this is equal to, so this is equal to k equal to 0 to k over n over 2, or n minus 1 over 2, and then there is minus 1 raised to later there. So that's 1 over 2 raised to n. That is a where did that disappear? Where did that disappear? This, let's see. 2n, so this is 1 over, did I have something? Yeah, there was this, no, everything is 0, 1, 2, 3, 1, 2, 3. I guess it's there somewhere. Okay, k, n minus k. 1. Okay, we'll see. Okay, 1 over n minus k factorial and 1 over k factorial, and the other one is just x d by dx raised to n of x raised to n minus 2k. Okay, and I lost an n factorial. Do you guys see it? N factorial. Okay, we'll do this tomorrow. Okay. I'll finish this. There should be an n factorial here like this. So it seems just, oh, it needs a kind of. Did I miss? It doesn't seem like. Oh, no, it's okay. Oh, yeah, it's not there. Okay, yeah, this is okay, perfect. Okay, good. Sorry, this is perfect. Okay. Now the point is, yeah, so I pull this out. Yeah, so in the next step, I want to show that. Sorry. Right? So So what I do is actually I put in an L factorial. That's because I want to see this as a binomial expansion. I introduce an L factorial, so n factorial. So introduce an n factorial and divide an n factorial. Okay. So this is here. This is equal to. Okay. This can come out of the sum. So this is 1 over 2 raised to n factorial. D by dx as raised to n can come out. And whatever is remaining is a sum over k equal to 0 to n over 2 or n minus 1 over 2. And this is n factorial divided by n minus k factorial times k factorial raised to, there was a minus 1 here, right? I forgot that. Minus 1 raised to k. So this is x squared raised to n minus k and minus 1 raised to k. And is that visible? Yes. This is a binomial expansion. In fact, whatever we did earlier. So this whole thing is nothing but 1 over 2 raised to n, 1 over n factorial, d by dx raised to n times x squared minus 1 raised to n. So that's called the Rodrigues formula. This is a convenient formula. So, right, for given n, write this, take n derivatives, you get a polynomial, and that's your this is called Legendre polynomial. So this is called Rodrigues formula. That's all. Thank you for allowing me to go further. Glad that I finished this, otherwise I'll have to recollect. Don't worry about the details so much. I won't be asking you guys to derive this in the exam, but the techniques that I used is very common in special functions. It's a good thing to get used to. You'll see this again and again, but most probably you'll never ever derive it. But these are good techniques, so you'll play around with it whenever you work in something else.